So this is the last theory video. We're going to go over types of metal bonding, Vesper theory, and the little bit on polarity that we covered. I'm not going to spend too much time on this. We're not going to go into too much detail, or I'm not going to explain it in as detail as I probably should be. But that's just because A, I'm kind of lazy, and B, and more importantly, most of this will not be the questions that will be on your test are very similar to the assignment questions, so we'll spend more time explaining those in detail. We're just going to quickly touch on the main points of the different types of bonding, and then we're going to move on. So, bonding. So the first thing we have to differentiate is between intramolecular forces and intermolecular forces. There will be a question I think on this on your test. Intramolecular forces are forces that exist in between atoms of a molecule or compound. So this is an intramolecular attraction between the hydrogen and the chlorine. So this can be said to be a covalent bond right there. And then intermolecular forces are the forces that exist in between the molecules. So this is between two molecules of HCl. So this bit of attraction right here. Most intermolecular forces are weaker than intramolecular forces. So, for example, the intermolecular forces here would be a dipole-dipole force. So this delta positive plus delta negative charge slightly attract each other, and therefore the bond is formed. There was a question in class about the difference between force and bond, and they're the same thing, right? The bond, quote-unquote, bond is essentially because there's a force in between them. That's what defines the bond. There's no line actually connecting those two atoms. In reality, there is just a force of attraction between them that we call a bond. Stronger the force of attraction, stronger the bond. So it's important to know the difference between the two, because otherwise things might get a tad bit confusing as we go forward. This is basically a review of grade 11. There will not be any questions on it on the test. This is just to review that the Mg and F2, realistically, we can consider this in terms, instead of your shells that we borrowed the electrons from, now we're going to consider them in terms of your orbitals. So we know that Mg has a 3s2 electron, and one of those electrons moved to the 2p of one fluorine, and the other electron moved to the 2p of the other fluorine, automatically changing spins as they do so as necessary. That's not something that we have to be concerned about, really, to form an Mg2 plus ion and two F minus ions, which then have electrostatic or ionic bonds between them because of the positive negative forces of attraction here. So these all have achieved noble gas configuration, more specifically, which noble gas again? Neon configuration, sorry about that, and therefore they are stable, which is what promotes this bond formation right here. The only thing we need to know about this is how to write now electronic configurations of ions. Usually there will be noble gas configuration, so it's super easy to write. You just write like neon, 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 and there may be some questions where you don't really exactly achieve noble gas configuration, for example with the transition elements, but we'll talk about that when we get to the assignment. So ionic solids are crystalline, smooth, shiny surfaces. They're hard and brittle. They're not conductors of electricity and heat because they don't have any free electrons. The ions are tightly the F minus ions are tightly holding on to these electrons, and they're not free to roam around and conduct electricity. They have high melting points because the bonds that are formed between them are fairly strong. They're of a strong level. Next, molecular solids, and here's where the key difference comes between intramolecular and intermolecular bonds. We have covalent intramolecular bonds, but molecular intermolecular bonds. So what does that mean? Covalent, so the example of this is HCl. The electrons are being shared between H and the Cl. That makes it a covalent bond. However, the intermolecular bonds here are van der Waals forces. So van der Waals forces, dipole forces, or hydrogen bonding, and this depends on what kind of molecule it is. So again, we've covered this in grade 11. We'll briefly recall that first to differentiate between ionic and covalent. So how do you tell if HCl is ionic or covalent? You compare this to an electronegativity series. We're about 0. I used to think it was 0.5, but 0.4, 0.5, let's say, I think, is a covalent bond, whereas 0.5 to 1.7 is a polar covalent bond, and 1.7 and above is ionic bond. So again, this is just looking at the electronegativity difference. If you don't really have to do this because, or if you do, I will be providing you with the periodic table with the electronegativity values. So that's fairly, again, just looking at electronegativity to tell whether, like NaCl, how do you know it's ionic? You compare electronegative differences. HCl, how do you know it's polar covalent? You look at electronegativity differences, right? And so nonpolar covalent molecules have van der Waals forces, so very weak. So this is example, a good example are all like hydrocarbons without functional. Okay, you're not gonna understand that. Carbon-hydrogen bonds are nonpolar covalent bonds. For example, C with hydrogens attached to them. Another good example of nonpolar covalent bonds are like any diatomic, so I2, O2, N2, Cl2. This is why most of them are gases at room temperature, because there's not much force of attraction in between them, and therefore they are gases because they have low boiling points and they have low boiling points, so they're gases. That's right, low boiling points. Yeah. Yes, they have low boiling points. Because, but if you look, okay, I2 is a bad example because it's actually solid. That's just because of the mass. If you look at O2 or N2 or like F2, these are all nonpolar covalent bonded compounds because there's zero electronegativity difference, so there's almost perfect covalent bonding, and therefore no dipole. So the forces in between them are van der Waals or London forces. Polar covalent have dipole-dipole. So this is, for example, an HCl. This will have a positive, negative polar covalent, means there is this partial charge separation. So the delta is a Greek letter. You can write D instead for delta. And this will attract a positive charge on another molecule. So as we saw before, this is the intermolecular dipole-dipole force. And then we also will hopefully remember hydrogen bonding, which is a special kind of dipole-dipole force that occurs when you have an OH and HF or an NH bond. So this charge separation is very big, and therefore it will form significant bonds to other similarly charged molecules. That is why water is a liquid at room temperature and has a relatively high boiling point of 100 degrees Celsius because of these hydrogen bonding forces. And so the order goes nonpolar covalent, van der Waals forces the weakest, then come dipole-dipole, then come hydrogen bondings, which are the strongest type of molecular forces. So that's important to know. And again, this directly corresponds to trends in the melting point and boiling point, right? Because the stronger the bonds, higher the melting point. So, I mean, although I do say that the trends are corresponding, and like hydrogen bonding, water has a high boiling point. This is all relatively speaking. In the grand scheme of things, if you compare them to ionic solids, etc., they have very low boiling points because any kind of molecular force is weaker than an ionic bond in all the bonds that we'll be talking about. So these molecular solids have the lowest melting and boiling points among all the classes that we're talking about. Again, relatively there is some variation in between, like polar, non-polar, etc., etc. Hydrogen bonding, etc. Next one, we briefly mentioned this before. Metallic bonding occurs in the between the atoms of a metal, like iron or zinc or sodium even, and it represents sodium ions that are basically held together with electrostatic interactions with free electrons. So there's an electron C, which kind of is the glue that holds all these atoms together, and they also share these electrons, but throughout the entire structure of the metal. So because there's free electrons, conductivity is high. Because you have this kind of atoms with kind of like glue holding them together, you can push them down one on top of the other. So its malleability was the ability to make thin films of these metals. So that's how we got the gold foil, because it was able to be beaten into a thin film. Ductility is to roll into a wire. So that's why it's easy to make copper wires, and it's hugely useful. They have high melting points and boiling points, around the same order as ionic solids. And there are some trends that we have to remember. So Mg2 will have a higher melting point and boiling point than sodium, for example. So S2 elements have a higher melting point, boiling point than S1, because these are more charged ions, right? So it's Mg2 plus, and each Mg2 plus contributes 2 free electrons. So the more free electrons, the more glue basically, and therefore more the melting point, or higher the melting point and boiling point. Again, transition metals, we noted the trend that more unpaired d electrons correspond to a higher melting point, except, so if we do scandium, titanium, vanadium is peak, and then we have a lower copper, manganese, because these two, chromium and manganese have a 3d5 shape, which kind of stabilizes them. Then we have iron, and then we slowly decrease until we reach zinc, because here your number of free electrons is decreasing because you're getting pairing of electrons in the d orbital. Zinc has the lowest, even lower than manganese, because it is a 3d10, completely stable, 0 unpaired electrons, 0 free electrons, so it's not really the same metallic bonding to the extent as the other metals have. So vanadium would be the highest there. The last one is network covalent solids. The main examples we're going to be doing are the ones with carbon, but again, carbon, silicon, germanium, all of these elements form network covalent solids. They form long, extensive networks where the entire structure is one molecule, basically. So if you take the case of diamond, the entire diamond is basically one entire molecule, because there's just a bunch of carbons that are attached to each other in equal ways. So this carbon has 4 covalent bonds to 4 other carbons, which again has 4 covalent bonds, which again has 4 covalent bonds, and so on and so on. And it's just one big molecule. Graphite, there are some differences. Graphites are like sheets that extend indefinitely in space, but there are like stacked upon stacked of layers. So technically, there are van der Waals forces between these sheets. So technically, graphite has a lower melting point than diamond, but we're not going to get too much into this. Just know that molecular solids have relatively super high melting points and boiling points, the highest. So diamond, for example. And then that's all we have to talk about for bonding. The next thing we're going to be focusing on is reviewing Lewis structures. So we have to know how to draw Lewis structures for different atoms. And hopefully this is a review from grade 11. We will be talking about one extra thing, so I think that's coming. Yeah. So I don't know which one you want to review here. Let's just do H2O for simplicity. So you write H2O, you identify the central atom. We know that's oxygen because there's only one of it, and it has a higher, so it can form more bonds than hydrogen. So whichever forms the most bonds is usually in the center, because all the bonds are coming out of the center. So we count the number of electrons, or valence electrons, for oxygen. So oxygen has 6 valence electrons, hydrogen has 2 valence electrons each, and then that's 8 electrons in total. There's no charge on this, so therefore we don't add anything, so we start off like this, and then we're going to add 8 electrons. So there's 2 bonds here already, so we got 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 electrons distributed around the H2O molecule, and this is the structure of water. We'll add on to this with Vesper theory, but this is basically how to draw Lewis structures, more or less. All right, you count the total number of electrons, you put the bonds in as required, and then you add the lone pairs, starting from the most electronegative, building up towards the less electronegative elements. So, important rules: hydrogen can only take a maximum of 2 electrons. It's impossible for hydrogen to have more or less. Oxygen, so the cannot overfill series, CNOF, stands for cannot overfill, always gets 8 electrons without fail, so that has to be a requirement. All those 4 elements, if they're present, have to have 8 electrons. Beryllium and boron are exceptions because they can have less than 8. They can have 4 or 6 electrons if needed. Things like sulfur, phosphorus, chlorine are exceptions because they can get more than 8 electrons as needed, depending on what's stable for them. And what that means is we have to work with formal charge. So formal charge is, there's different ways of defining it. Again, if you look up something where you have non-bonding electrons minus bonding electrons, it's kind of the same thing, or bonding electrons divided by 2. Essentially, you would like to do the valency, which is the number of valence electrons minus number of lone electrons, not lone pairs, actual number of lone electrons, minus number of bonds that the atom has. So for example, let's do some of these questions. So I like SO3 2- because it demonstrates this concept very well. So SO3 2-, you would start with 6 plus 6 times 3 is 18, plus 2 because there's a charge of 2-, so it's got 2 more electrons. So this is a total of 26 electrons. So you would start with SO3 like so. You would add, this is 2 electrons each bond, right? So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. This would possibly be, so looks like everything has 8 electrons here. Everybody's happy. The sulfur has a lone pair, so it also has 8. You might think that this is a good structure for SO3 2-, and you wouldn't be too off, but unfortunately we have to calculate formal charges to make sure that it's minimized. So sulfur and oxygen are both electronegative atoms, so they want to have a negative formal charge. So formal charge is basically, so we know that SO3 2- has an overall charge of 2-, right? And that 2- charge is coming from, we don't know where it's coming from right now, but the formal charge is basically calculating an individual atom's contribution to that 2- charge. This, as a whole, has a 2- charge. And you might ask, okay, where is that 2- charge coming from? I don't see any negative charges on any of these atoms. All of them have 8 electrons. So where is this 2- coming from? This is where you have to calculate formal charge. So formal charge is, again, you do 6 for oxygen minus 1, 2, 3, 4, 5, 6 lone electrons minus 1 bond. So the formal charge of oxygen is -1. This oxygen also is 6 minus 6 minus 1 is -1. In the same manner as this oxygen, 6 for valency, 6 lone electrons, 1 bond. Similarly, 6 minus 6 minus 1 is -1 formal charge for oxygen. And if you calculate the sulfur valency is 6 minus 2 minus 3, because minus 2 minus 2 lone electrons and minus 3 bonds. So this is +1. So right now, the -2 charge is coming mostly from, 3 oxygens contributing -1 each, and the sulfur is contributing +1. Ideally, though, the sulfur wouldn't do that, and because sulfur is also fairly electronegative, it doesn't really want to contribute a +1 charge. It also wants to be negative. However, oxygen is more electronegative, so it's going to hog all the negatives. But what you can do is you can get rid of this -1, +1. And this is, again, only possible because sulfur is a bigger atom. It can accommodate more than 8 electrons. So what I'm going to do is I'm going to take off one of the lone pairs from the oxygen, and I'm going to make that into another bond between sulfur and oxygen. So now if we recalculate formal charge using the blue, for the blue one, you have an oxygen of 6 minus 4 lone electrons minus 1, 2 bonds, which is 0. Sulfur has 6 minus 2 lone electrons minus 4 bonds, which is also 0. So now the formal charge for oxygen is 0, sulfur is 0. These two oxygens still have a -1, which makes the overall charge -2 as required. But now the negative charge is coming from 2 oxygens instead of 3 oxygens with a negative and 1 sulfur with a positive. That's unfavorable, and so there will be double bond character between. If you look at the bond length between the sulfur-oxygen bond, there will be one bond. We didn't talk about resonance, but this bond length will be closer. It'll be shorter than a regular single bond would be because there is double bond character between that sulfur and oxygen. So this is an accurate Lewis structure of SO3 2-. And we can repeat the same for the other ones, ClO4-, ClO3-, PO4-3-. I will do so on another page, PO4-3-. So phosphorus, again, 5 plus 4 times 6 plus 3 is 24, 29, 32. 1, 2, the bonds first. Now you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Technically now I have all 32 electrons. Everybody has an octet. The total charge of this, but again, the total charge of this molecule has to be 3-. I'm going to figure out where my 3- is coming from. Oxygen, again, at some point, you just kind of like, if you do these like 2 or 3 times, you kind of understand that if an oxygen has 3 lone pairs in a bond, the formal charge is -1. If it has 2 lone pairs in a double bond, the formal charge is 0. So again, 6 minus 6 lone pairs, lone electrons minus 1 bond is -1. 6 minus 6 lone pairs minus 1 bond, -1, -1, -1. Phosphorus is 5. Minus 0 lone pairs minus 4 bonds, so that's +1. And again, phosphorus doesn't really like to be a positive because it is a non-metal, and therefore you will erase one of those electrons, form an extra bond, which makes oxygen 0, phosphorus 0. The total charge is still -3 from the other 3 oxygens, but this is a more stable structure. And again, phosphorus here has 10 electrons bonded to it, but that's okay because it's not CNOF, and it's big enough to accommodate those 10 electrons, so that's fine, so that's allowed. Next one, ClO-. We had, so it doesn't matter which one's the central atom here, it's just ClO. Here you have 7 plus 6 is 13 plus 1, 14 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This entire thing has a charge of -1. Let's see how that charge is distributed. We have a -1 for an oxygen, and we have chlorine. Both of them have 8. So first we have to check, most importantly, does oxygen have 8? Yes, chlorine has 8 as well, so let's check. Chlorine has 7 minus 6 minus 1, which is 0. So right now the chlorine has a 0, oxygen has a -1. That's a total charge of -1. I would say this is happy. What happens when you take a lone pair from the oxygen and you give it to the chlorine? Right, so let's say we do that. Say I've removed a lone pair, I've made a double bond. Now oxygen has a formal charge of 0. Chlorine has a formal charge of 6 minus 6 minus 2, -1. Chlorine is fine with the 10 electrons because it's bigger. Oxygen still has 8, so we're good. But now chlorine has a negative charge, oxygen has a 0 charge. So which one is more favorable? You have to look at electronegativity. Oxygen is more electronegative than chlorine, so we will prefer to keep the negative charge more towards it. and so therefore there is no double bond character in there. The oxygen will keep the lone pairs to itself, and this will be the correct structure of ClO with a single bond. Is that all the space I have? Let's try another one, ClO4 minus. Keep wary of the time. We might have to do Vesper in a separate. What did I talk about for so long? I don't even know. Okay. ClO4 minus, central atom is chlorine, 4 oxygens on all the sides. Here we have we count the electrons as 7 plus 24 plus 1 is 32. Very similar to the phosphorus case, we have 1, 2, 3, 4, 5, 6, and we have 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Everybody has 8. We are almost happy, except for the fact that now we have -1, -1, -1, -1. Chlorine is a +3. This is not at all ideal for chlorine. The overall charge is still 1-, but this is not the way to go. And therefore, in order to ease the formal charge on chlorine, we are going to form multiple double bonds, one over here, and one over here, thus making the formal charge on chlorine 0, these oxygens 0. Chlorine now has, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 electrons. It's unclear at this point. 14 electrons might be too much for chlorine. You could draw the structure. Realistically, if you look at the molecule, there might be a kind of bonding like this, where chlorine still has a +1 formal charge. 2, 3, 4, 5, 6. But now it has only 12 electrons, which is not as bad as 14. Again, it depends. Either way, I will give you marks for it. There's no way to really know. And it's not like a rule. Again, I know it's nice if I just tell you this is what it is, but unfortunately that's not how atoms exist. ClO4 will technically exist in a flux between 3 double bonds and 2 double bonds, and depending, it will keep changing. The double bond will form and disappear. There's weird stuff that happens in the subatomic world and in the world of atoms, so you can't really tell that this is the exact structure of the molecule. It's more of like it's weird. Again, so either way, I will give you the marks for this one. Just make sure you're calculating the formal charge and putting at least 2 double bonds on it. Again, is there going to be exactly 2 double bonds? Why not? Could there be 1 double bond? Yeah, hypothetically there could. Again, constant flux between the bonds formed and bonds broken. So we cannot know for sure. But that is that. That was the Vesper theory for these guys, including the formal charge. So we'll talk about, not the Vesper theory, the Lewis diagram, and we'll talk about Vesper and polarity next, before we get to the homeworks. Alright, so see everybody.